começar, né? Já deu 5 agora. 4. Aí.
Okay, so the next speaker is Lucas Afonso, here from São Paulo. He did his PhD with us in our group, and now he is a postdoc here in the Department of Statistics, here in the same institute. And he will speak about the notion of contours from long-range Ising models.
Okay, so thank you, Rodrigo. So today I want to talk about, give some historical overview of some part of the literature that I've been in contact with for some years. And our story starts with the Ising model, that in a modern way to define it, it was introduced by Lenz and Ising and studied by Ising, but we define it by a family of Hamiltonians with boundary condition. I guess many of you already saw this. And the most important examples that I will talk about are the nearest neighbor case, the nearest neighbor Ising model, where the JXY, the coupling constants, are chosen in this way. The long range Ising model with polynomial decay, when alpha needs to be larger than d, and also this constant J needs to be positive for the model to be ferromagnetic. So a little bit about the early history of the model. So what happened is that Ising solved the one-dimensional nearest neighbor Ising model, and then he concluded erroneously that there would not be phase transition for any dimension for this model. And then Pyros showed that this was wrong indeed. In this paper in 1936, and this paper was people didn't look too much at this paper right away. But what happened during the 40s is that we had two breakthroughs, one by Kramers and Vanier, and the other by the solution of the pressure by Onsager, that predicted the same thing that Pyros did with his argument. And then the rigorous story of the Pyros argument it started in these two papers, did independently by Griffiths and by Dobrushin. And a nice piece of the history, I think, of this model is that on MathSciNet you can find a review by Pyros of the paper by Griffiths, because in the paper by Griffiths says that the Pyros argument was evidently incorrect, but Pyros says that this was actually just some the error was essentially one of wording. And if you want to see this review is on MathSciNet. So, and the idea of the Pyros argument was to give what many of you know as Pyros argument. So you need to find a geometrical representation of a spin configuration that we call contours. In the case of the usual two-dimensional Pyros argument, the idea is just to separate each sign, each minus and plus. This is called the spin flips because you are changing the sign. And you separate it by some bond here, and then for you to construct a Pyros contour, you just take the connected components, and you also have to give a fixed way to cut these joinings here. And then if you do this, then you have a collection of Pyro's argument. So the idea for the Pyro's argument to work is that after you have your ingredient given by the contours, is that you have to have an energy estimate. In this case, for the nearest neighbor Ising model, you have the estimate actually is an inequality. You can break for a given configuration. If you associate a family of the Pyro's contours as we showed previously, then the energy normalized by the energy of the ground state is exactly the sum of the length of the contours. And then you also need to have an entropy estimate counting how many of these you can see. And after this, with an energy estimate and entropy estimate, you can show the phase transition. So what happens some little time after that is that Ginibri and Gross-Manuel noticed that the Pyro's argument was also good enough to show phase transition with the same contours, not only for nearest neighbor neighbor interactions, but also if we consider more general interactions, allowing also long-range interactions. For the case of a two-body interaction, for instance, what happens is that for their argument to work, they need this condition to be satisfied. Basically, that the nearest neighbor coupling J should win from this term right here. That is the long-range part. And if you assume that the potential decays is something polynomial, this condition implies that you need to have something that decays as alpha larger than d plus 1. So as you can see, at this point in 6.6, you can conclude phase transition for using a Pyro's argument for models with decay larger than d plus 1. And of course, there is a remaining range between d and d plus 1. But right in the next year, in 67, the Griffith's inequalities appeared, and then the problem of phase transition is solved, because if you have phase transition in the nearest neighbor case, of course, with the field, magnetic field equals to 0. If you have phase transition in the nearest neighbor case, of course, you also have phase transition with for the long range case with alpha decaying faster than d. Okay. So what happens is that this condition right here for the Pyro's argument to hold is somewhat optimal, as shown by Van Etter in this paper, and also by this paper by Biscup, Chase, and Kivelson, where they both showed they can show that if you try to add an antiferromagnetic interaction with an intermediate decay between d and d plus 1, the magnetization needs to be 0. So as you can see in this condition right here, I put the absolute value of the potential. So this, of course, this condition ignores the sign. So okay, so this result is the result is this. So, but there is the problem for the one-dimensional case, because to use Griffith's inequalities, you must have some model to compare. And for the one-dimensional case, the short-range Ising model doesn't have phase transition. And what happened is that this result of uniqueness was extended, for instance, by Ruel in this paper in 68, where the condition for uniqueness in this case can be read as this one for two-body potentials. And this implies that decay can be put to be long range, but should decay faster than this. So they should decay like this. And then Katz and Thompson in this paper right here, they put forward the question of if in the remaining region maybe you should have a phase transition. And what happened is that Dyson solved the problem, again with the strategy of comparing, or using correlation inequalities, comparing with another model. And what he did is that he introduced what is known today as an hierarchical model that only works for the case between 1 and 2 for the decay. And also another interesting historical fact is that you will find in this paper on the references that in a private communication, Thompson said to him that he believes that for the case where alpha equals to 2, there should not be phase transition. And as we know, this result was indeed wrong, because sometime after that, in 1982, we have the first paper by Fröhlich Spencer. Okay, not the first one on this problem, but the paper on the one-dimensional model in 82, where they solved this problem, showing the phase transition, but with now a contour argument. And many years later, we have an extension of the Pyros argument using also contours in the one-dimensional model in this paper right here, 2005. And the idea here in both papers is to organize the set of all the spin flips, as we did for the multidimensional case, in some sort of contours. And this version that I'll show to you of the definition in Fröhlich Spencer comes from a paper by Imbri, where he studied the decay of correlations in the one-dimensional model. And the first thing is that he calls a subset of the spin flips irreducible if you have an even number of spin flips, and if there is no decomposition of this set such that this distance condition between them is satisfied. So this means that if you cannot decompose the set into distant parts, okay? And what he shows in this paper is that there is a unique way of partitioning the spin flips into irreducible subsets where this condition of separation is satisfied. So if you look to the paper by Cassandro, Ferrari, Merola, and Perzutti, they did something. So they still studied the spin flips, but now they introduced a geometric picture of these spin flips. So what they did is that they defined some triangle configurations, and the idea is that you divide the spin flips using these triangles. Okay, the triangles are like the heads, okay, of the spin flips. And what you do is that you organize triangle configurations. There is a way to associate to it configuration a triangle configuration in an ambiguously way. And what they did is to organize these triangle configurations into their contours. And this version right here that I'm presenting you, I adapted from Bruno Kimura thesis. And they ask that when you organize the triangles, so what you get in the end is a partition of the set of all triangles, and that they should be well separated. I'll not delve too much on this because I think Pico will talk more to us about this kind of thing tomorrow. But the idea now is also the same. You need to separate the spin flips, in this case the triangles, into subsets that are sufficiently well apart. So what do you get? In the case of Fröhlich-Spencer, what you get is that with their definition, you get that an energy estimate, that's a lower bound on the energy, that now it's not controlled with respect to the size of how many spin flips you have, but they control it with this quantity right here that is just the sum of every, so for each n, you take the minimal number of open intervals of side lengths 2 over n covering the set. You sum this quantity over here. This is a quite strange quantity to look at, But they managed to show that when you try to flip a contour, to extract a contour from a configuration of contours, then this quantity describes the remaining energy. And after that, they need also an entropy estimate, and they use that same quantity to control the estimate. So if you consider all the sets of spin flips, that the zero is in the interior, and that quantity over here is bounded, then this is exponential of something depending on n. And then you proceed to do the Parallels argument in the same way. Okay, but remember, this all works just for alpha equals to 2. They made this for alpha equals to 2. So what happened in the paper of Cassandra, Ferrari, Merola and Prezzuti is that they, you wanted to make some? Yeah, the paper is written for alpha equals to 2. So I don't know if their argument works for any other, but when I read it, it uses alpha equals to 2. So so what happened in this case that they extended for other range of alphas, and now they get the difference of when you erase a contour in terms of another quantity that depends on the triangle. So this has a more geometrical interpretation. So the difference of energies depends on some function of the triangle configuration. And this quantity is this expression over here. Okay. And just to get a feel what this means, what they managed to show is that if you define, okay, this is a mistake, so it was supposed to read L to the power 2 minus alpha, so it's L to the power 2 minus alpha, okay. So what you get if you define this quantity over here is that that quantity over there, the energy here of a triangle configuration, is larger than something that depends on the decay. And they managed to show this result if the nearest neighbor interaction is large, and there is a restriction in the alpha. So the decay can be 2 in this case of their paper, and they can also reach some other region right here. So and okay, so after that, without the nearest neighbor constraint, but you need to put another constraint on alpha. There is this result by Bissacco, and Van Etter, Kimura, and Roussel, where they take this hypothesis here away, but they need to further restrict the range of alphas where they apply. And the contour, the triangles give a more geometrical, as I said, give a more geometrical interpretation of the problem. And what they managed to show is that the Littin and Pico also showed that although the triangles are nice, the energy bound in terms of the contour in that way that I showed you, something like this, cannot hold for the whole region, but you can extend for the whole region. They show it, but not in terms of the triangles. So, and also for and what they do for the entropy now. What they need to do is that they control this quantity right here that has an interpretation of entropy, and with this you can finally show the Parallels argument in one dimension. And what happened is that with their extension of the Parallels argument, they opened many possibilities to study different problems. For instance, they studied, I will just cite a few, but they studied this problem. They studied the cluster expansion and also the distribution of the phase separation point. And they also could prove phase transition in the Ising model with a random field. And I must tell why this is nice, because there is a very famous result on uniqueness by Eisen and Ver that works only on dimension 1 and 2. But what happens is that their uniqueness for long-range systems in dimension 1 and 2 depends on the decay. What they say for dimension 1 is that if alpha is larger than 3/2, then there is uniqueness. And what happens is that with the extension of the Parell's argument that they did, they can show the phase transition for the random field model in a region, not the whole region of the parameters, not on the complement. They cannot show in the whole region, but they can show in some small region that can get close arbitrarily to the let's say the critical value where you have uniqueness. So here is equal. Okay. So, and this was noted by Eisenman, Greenblatt, and Lebovitz, where they said that exactly what I told you, that it's curious because although they cannot reach the whole region of the intervals, they can reach, they can get to the let's say the critical value. So back to the multidimensional models. As I told you, the problem was, let's say, closed for general interactions. But as I told you, the counterexamples of the that Van Etter and Biscup, Shays, and Kivelson found were anti-ferromagnetic. So the idea is that when you put a ferromagnetic interaction long range, you should still be able to prove phase transition using directly using a Parell's argument. And this is where we started our investigation. We started first by looking at this paper of Park, where he tried to extend the Pirogovsky theory. And this he has the same problem. He has some problems related to the previous approach, because here he is insisting on the contours. Okay, they are not the Parell's contours, but they are the Pirogovsky contours that were devised to work for finite range interactions. So, not surprisingly, he gets a problem with the decay, and he needs to ask the decay to be larger than 3D plus 1. But he managed to extend the Pirogovsky theory, so he doesn't assume a symmetry of the interaction, and he can also consider any finite state space. For instance, in this paper, he can, in the following paper, in the second paper, he can study the phase transition in the Potts model. And then, regarding the contour argument, we have this paper by myself, Sako, Eric Endo, and Satoshi Handa, where we studied the long-range model with a decaying field. Okay, and the thing about the decaying field is that you cannot use correlation inequalities to study to conclude phase transition on this model. You should have a Parell's argument. So this is why we were interested in this problem. And also now we have this reprint also by Rodrigo Sacco, João Maia, and myself, where we studied the problem of phase transition for the long-range Ising model, but with a random field. Here we have the dimension to be larger than or equal to 3, and this will be part of the talk of João on João PhD defense on Wednesday. So what is the idea of the construction? The idea is the following. So you cannot, for long-range systems, we cannot separate things into connected components, because since the system is long-range, the problem is not if they are connected or not. The problem is that if the interaction energy between is large or not. So how we define the contours, how we deal with this problem. So first we need to introduce a notion of incorrect points. This comes from the Pirogovsky theory, and is the definition is the following. So given a configuration, a point in ZD will be called plus or minus correct for this interaction. If all the points in a ball of radius 1, the sign of the configuration is always equal to +1 or is always equal to -1. And the boundary of a configuration, now it's a subset of ZD, will be all the points in ZD where the points are neither plus or minus correct for the configuration sigma. But what this means in a figure? So again, I took the same configuration. You suppose that everything outside is plus, so everything is plus. And what you get is this quantity over here. And as you can see, and this is quite different from the usual Pyros contours, because in that definition we had many connected components. Here we only have two different connected components. Okay, but this is the thing that we'll work on. So the set of the boundary of a configuration. So the set of all incorrect points of a given configuration. Okay, so as I told you, there is you can't get good results if you try to separate them into connected components. So you need another way to partition the sets. And this was the definition that we used to solve the problem in the decaying fields. We called it MAR partition. So the idea is that you fix real numbers, MAR. These are the parameters, okay? And then for each configuration with a finite boundary condition, so this condition is always satisfied if we are looking to configurations that are equal to plus or minus in the infinity, okay? So so exactly in the case that we are concerned with for the Pyros argument to hold. And then we say that a subset, a collection of subsets of the boundary is an MRA partition if they satisfy this condition A, if they form a partition of the boundary, and moreover, if they satisfy another geometrical property, that if we take two different elements of gamma, then and if I take the complement, the connected complements of the connected components of the complement of one of them, then the other one must be signed in a unique one. Okay, this is confusing. So let me show a picture. So for instance, suppose that we have this figure right here, and I wanted to partition into something, okay? And I choose to partition in the following way. So gamma, this gamma will be one element. So note that it may not be connected, and gamma prime will be the other element of the partition. So the problem with this partition here is that it doesn't satisfy condition A. Why? Because if I take the green region and I take the, you cannot see that it's green, but if I take the region gamma, okay, and I take the complement of this region, we have one connected component, this white region, two connected components, this third connected component, this white one, and there is this another unbounded connected component right here. And as you can see, gamma prime occupies three different connected components of the complement of gamma. So this is not allowed. So in order to this partition to satisfy condition A, so it must be divided. This one must be an element, this must be another element, and this must be a third element. And also, we needed to introduce a notion of separation, as they did in the one-dimensional case. So for the M array partition, the notion is the following. So for any element, there will be an n that is can be 1, but is bounded, it's upper bounded by 2 the power r minus 1, and a family of subsets of gamma, okay, such that you can write gamma as the union of these sets. And for all distinct pairs, we have this condition of separation. It's a quite cumbersome condition, but you said that the distance of these components are larger than m times the minimum of the maximum of the diameter of them to some power a, okay? Okay, again, what this means. So again, let me try to give you an example of something that does not satisfy condition B. Let's say that each one of these components here have a diameter n, okay? And this one have a diameter, let's say, 10 times n, okay? Let's suppose that I wanted to define an array partition given by these two dashed red lines. So I needed to check this condition, and let's say that my parameters are like r equals to 2. So I'm only allowed to partition this set into 3 parts before checking this condition. And then I proceed to do this. And then what I found is that since this element right here has a diameter 10 times n, you cannot partition it into 3 parts that has diameter less than n. And since each one of them also has diameter larger than n, you cannot partition these into 3 parts with diameter less than n, since they are quite well separated, but not so much. And then when you plug this, what you get is that in order to satisfy the condition B2, their distance should be larger than m times the minimum of the maximum diameter of each one of these partitions. In this case, it would be something like 3n, I don't know. And in this case, will be something like n. So the distance should be larger than n times n to the power a. And as you see, I put this conveniently. The distance should be not to be less than n to the power a. So this is not allowed. Another thing that is not allowed is something like this. So again, we have the same setting, but now suppose that each one of the components have let's say okay, here I have again 10 times n, and here I have here I have diameter n, here n, diameter n, everything diameter n, in this example right here. So what happens in this case is if each one of these components have diameter n, if I partition this set into 4 parts, okay, and then I put into this condition on the distance, I can check that this is satisfied for these choices for this choice of m. But the problem here is that I had to partition the set into 4 parts, but r is equals to 2. I'm not allowed to do this. So again, this is not this is something that does not satisfy condition B2. So okay, I gave you only examples that does not satisfy our definition. So the question is there something that satisfies our definition? So before we proceed, what we use to construct the contours is always the finest M-array partition. We will show that there is a possibly non-trivial one in a minute. And what happens is that for the problem in question, we need to choose, we need to tune the parameters accordingly to the problem. In this case, we can choose A as being d plus 2 over the minimum of alpha minus d and 1. And as you can see, when the interaction alpha, when the k parameter of the interaction alpha is closer to d, then you get A to be larger, And since the separation condition B2 is something that goes to the power of A, this means that when the interaction is stronger, the contours should be further apart. They need to be uh, more separated. And R is chosen in this way, in this fashion. So as you can see, A and R in the end are constants that will depend only on the interaction, alpha and D. And M is also something that will depend on alpha and D, but the choice appears during the calculations. Okay. And as you can see, if you remember the definition that I gave from Froelich-Spencer using the diameters, okay? If I choose A equals 3 halves and R equals to 1, the condition B2 is exactly the condition that they gave for the separation of the spin flips. So, okay, going back to the problem. How can we show that there is a possibly non-trivial one? So the idea is based on what is called a multi-scale argument. So the idea is that at each scale, so you have a notion of scales that you will you evolve, and then at each scale you do something and then you go to the next scale. You do something and you go to the next scale. This is the idea. Okay, but it's better to show pictures, okay? So suppose that we have these gray regions as being the region of incorrect points that we want to break into connected regions. Sorry, into an MRA partition, okay? Let us choose M equals to 1 and R equals to 3. So this means that I can only partition things into at most 7 parts, okay? So what you do first is that you take away small components. So the idea is that you take away every component that has uh, less than a fixed number of points, and their distance is less than this. So they are not exactly connected, but they are small and they are close in some sense, because this is, as I said, M will depend only on alpha and D. Okay, and then you start with the after you do this first cleaning of the set, then you will start with the multi-scale argument. So what is the idea? The idea is the following: you first cover the remaining set with cubes of side length 2 to the power r, and the center of the cubes must be on ZD. If you make this cover, so if you make the discovering with the cubes, they may overlap. So what you do is that you take some minimal covering, and after that you will produce graphs where the vertices, the vertex set are the cubes of the minimal covering, and there will be an edge between each cube if their distance is less than this, m times dA to AR. And what you do is that you will take, of course, this graph that you build may have many different connected components, and it will have different connected components exactly when the cubes are well separated. So the cubes should be the distance between them should be larger than this. Okay, so there is no edge between them. And then what you do is that you look to the connected components of this graph, and you take only the connected components that have less than 7 cubes in the vertex set. For instance, this guy right here will have only three cubes this component right here. So we will subtract it from the construction. Okay, so this is the remaining set. So what we do next? Then we need to upgrade the scale. So we go to, we make a cover with cubes of side 2 to the power 2 times r, and we also rescale the center. So the center should be inside ZD times 2r. Okay, so you have less cubes when you are going further in the scale. And then you have something like this. You take the minimal cover. Now this quantity right here, this guy right here, have 7 cubes exactly. So you subtract it, okay? And this is the remaining set. What? Okay, so you go further away on the scale. You repeat the procedure. You make the graph again. You update the edges. The edges, there will be edges in the cubes if the distance is small compared to the scale. So you see the distance changes with the scale here. The distance is changing with the scale also. And okay, in this case you have more than 7 components, so you do nothing. Then you go to further away in the scale. Now you have only five guys here, and then you finish the construction. What is the Mar partition then? The Mar partition will be the intersection of the cubes in that given scale with the subset that you covered. So this is the one that this part will be, let's say, this will be one contour, this one will be another one, this will be another one, and each one of the colors are different contours. So as you can see, they may not be connected. They may not be connected, but notice they may not be connected on the scale, on the first scale, but at each one of the steps, they come from a connected component of a graph in that scale. So what we managed to show is true that there are the main results on this construction is that we can actually have an exponentially many of them depending on the mass of the support. And also I need to make another drawing since it appeared there. We have, for these sets, we have a notion of volume that is the following. If I have, let's say, something like this is my lambda, okay? The volume of the set is the set that contains lambda and there is no holes, okay? So you just erase this. This is the volume of the set. And of course, if you have, let's say, 2 connected components, the volume may be non-connected, but it is a union of simply connected sets. So there is no holes on the volume. So if you try to count the contours coming from that construction, where the 0 is in the volume and the size of the support is equals to m, you can actually get an exponential bound. And the idea is quite simple. You introduce a generalized version of what happened in the Froelich-Spencer paper. You have this quantity right here that counts the minimum number of coverings, but instead of intervals, you use cubes. And then the idea is that you show that a contour, for it to be a contour, this quantity must be bounded, and the sets where this quantity is bounded and 0 is inside them is exponentially bounded. So this is the idea for the entropy. And also we have an energy estimate that is quite nice, that has not only something depending on the size of the support. This is more or less expected because it comes from the nearest neighbor contribution of the problem. But we also have two additional terms that represent the interaction between the inside and the outside, okay? And in this case, we have a very particular way of erasing a contour that Kelvin will talk about in his talk, and João also. We actually get something like this. When you try to extract a contour in a very specific way, the remaining energy is the size of the support plus these two other parts. So okay, 5 minutes. Uh, so what happens is that, as you saw, the definition is quite difficult. And what happened when João started studying this is that he introduced another version of it that works quite well, and it's easier to explain. The idea is the following. So you have now, you don't have a parameter R here, and he managed to do this construction for any given subset of ZD. It does not need to be a region of incorrect points. And the idea is the following. So yeah, I put a pause over here and there is nothing. Okay. Can you read this? Okay, so you have also the condition A, but for the condition on the distance, you have another thing for the condition on the distance. So the distance between two elements of the condition A is the same, but the condition on the distance is that they must be larger than the minimum of their volume to the power, oh, sorry. Yeah, so this should be larger than the minimum of their volume, the size of their volume, to the power A over D plus 1. Here, maybe you can see this. Power A D plus 1. So there is no need, there is no R, there is no, you don't need to break the set before checking the condition of separation. You just look to the volume, and this is it. And what is the definition between the previous one and this one? What happens is that the first definition that we gave actually produces much more sparse objects, because what happens is that the first definition only cares about the diameter. And what happens is, if you take, for instance, A to be this set over here, given by these hollow shapes, so you only have this shell over here of the cubes. Since the previous definition only cares about the diameter, it doesn't see that this quantity here has a small quantity of points. It doesn't. It just see its diameter. So what it happens is that when you try to break it in a MRA partition, for instance, if R equals to 2, with this choice of the parameters, you get a chain, a very large chain of hollow pictures. And in the case of João, when you look only to the volume content, then you can separate these regions that should contribute less to the problem. So you further separate the set. But of course, now you have to change the choice of the parameters. But again, you can make this choice also depending only on alpha and D. So it only depends on the interaction. And then in the paper, in the preprint that I showed you by Bissacco, João, and myself, we can show a similar result also using the multi-scale argument. Another contribution of João to this problem is the simplification of the procedure. Instead of using cubes with a scaled side length and cubes with a scaled center, what he did is that he defined these M cubes depending on a point X on ZD corresponding to this one that exactly partition ZD for each M, and they are exactly contained one inside the other when M is growing. Okay, so for instance, this is the cube with C3, and as you can see, you can partition it exactly using the cube C2, translations of the cubes C2. And in this way, you don't need to take minimal coverings. And what he do is the following. Again, the idea is the same. You will have to, you take the coverings at each scale, you will define some notion of a graph, and then you will take the connected components of this graph. And the idea here of João is you start here with that cubes, you take the covering, and then you consider a graph where the vertex set is given by the cubes, and there is an edge every time that the cubes have a distance less than this. Okay, this R is a parameter; it's arbitrary, and actually it's important only on some technical parts of the paper on the random field case. And then suppose that you have now let's say 4 different components, connected components of this graph. Okay. What João do is the following. You take a connected component, for instance, and then you look to the volume of the set that you are covering by G4. So it's just this shape over here, and you check if the volume of this component, let's say the volume of this component G4 is less than 2R D plus 1. I guess this is shown right here. So then every time you have a connected component of the graph where the volume is less than 2R D minus 1, you remove it. And then you take it, that this will be a contour. And okay, then you have something like this. So you remove this A1 part. And then you go to the next scale. To the next scale, you construct a graph, again, updating the edges, okay? And you only look to the connected components with volume less than 2 to the power 2 RD minus 1. So you also update the restriction on the volume. So in this case right here, you have too large volume, so you not take this away right away in this procedure. But since the cubes are invading and the volume is diverging, eventually you will subtract the remaining part. And what happens that if your region is something like this will be the MA partition by João. Thank you for your attention.
So, questions or comments? No.
Okay, so I like history of science.
Okay.
Okay, so you mentioned at some moment that in a paper of Dyson.
Yeah.
Okay, there is a private communication with Thomson.
Yeah.
Okay, you have something to know something which is important. That at that moment, Thomson was a young student. He was doing his PhD. So you imagine you are making a PhD and you go to Princeton. Okay, you go to Princeton and discover someone which is Dyson, which was at the moment a very important physicist, extremely important. Okay, and he asks you when you're a student, he asks you, what do you think about there's a transition in alpha equals 0, and you say, oh. Perhaps not. You don't know. You are 25, and the other is one of the most important experts in this kind of thing. You say, I don't know. I have no idea. And you have no idea. So there is no phase transition. So it's extremely important that in the history of this model, at a moment, Thomson wrote a memorial, okay, about cats. Cats is one of the most important scientists in mathematical physics and in probability. Feynman Cat's formula is cats, the same cats. Okay, so in the memorial written by Thomson, there is absolutely no mention about the one-dimensional model. Zero, absolutely nothing about this one, nothing. So no. this is strange because it was a very important
Even
result.
the paper
No, he
that
didn't
he wrote
mention.
with
No,
cats.
no, he
No,
mentioned.
no mention.
No mention about this model. This is published in Annal of Probability. So you can say Thomson. I mean, this is dedicated to cats.
Okay.
That Thomson. You're looking at the publication of Thomson, and you will discover this. There's absolutely no mention of this. This is extremely strange. Okay. Yeah. Okay. So you have to. I mean, when you say that Thomson think that perhaps there is no phase transition in the case alpha equals 0, you have to be careful. That is what in a specific situation where you are a young student, you are going to Princeton and you are speaking with some of the most important physicists of the moment. So, okay. Okay, so be careful when you say something like that.
Okay.
Okay, just to know that if you follow the history of the model, you'd say, there is something which is strange there. Because cats don't make mistake, okay, and you know to compute everything more or less. And cats say there is a transition, but Thomson perhaps say but perhaps there is no transition. I don't know. So we have to. Okay. Yeah.
So thank you for very okay, Aldo.
Yes, I would just like to make a comment about this research that you are doing here in São Paulo, and I confess that I was I didn't know that it was so advanced, let's say, because the problem with the d-dimensional Ising model with long-range decay, as you told in the beginning, when, by Griff inequality, it's clear that there is a phase transition because just the potential is growing. It's monotonic. The problem is the analyticity of the free energy of the pressure, because in the Ising model. In near-net neighbor, you can prove analyticity for beta sufficiently small and for beta sufficiently large, without problem. Let's say using cluster expansion. When you deal with the long-range interaction Ising model, you expect the same things. Yes, and in fact, it's absolutely easy to show analyticity of the Ising model with long-range transition for beta small, but for beta large, it's a mystery. But it seems that you have solved this mystery, if I understand well.
Yeah, we are writing a paper on cluster.
Seja, you are able to prove the analysis because the free energy doesn't depend on the boundary conditions. So you can use plus boundary condition. You are able to prove analyticity of the free energy of the pressure, the log of the partition function divided by the volume in the infinite volume limit using, for example, plus boundary condition when the interaction is long range.
Yeah, actually, this is we are writing the paper right now where we controlled the cluster expansion, and this is a consequence of the cluster expansion for this region. Of course,
because exactly the cluster expansion, you have to decide which are the contours to make the cluster expansion. So,
exactly. Yeah, exactly. So the contours that we are using for this paper are these ones from João. And yeah, on Wednesday. Yeah, but
yes.
Yeah, but the master, yeah,
yes, I read the master.
Yeah,
thesis,
exactly.
I was very surprised that this master thesis contained this result. Let's say that I don't know if physicists are so much interested in this problem because clear analysis of the why one need to show analysis of the free energy also for beta large. For me, it's important because I don't understand why it's possible for nearest neighbor and it's not possible for long range iteration. Yeah. So this is a very, very nice result that you are working on.
Okay, thank you.
The situation of this paper is the following. We have the cluster expansion, but okay, the situation. The first paper it was 2021, right? So the editor and gems disappeared. So I am communicating with the editor-in-chief because the people which was managing the paper, he left the journal. So yeah, we are waiting. They say they have 4 reports. We can expect as positive, but they don't have the decision right now for the first one. So okay, the random case, okay, we are submitting, and the cluster expansion that we were trying to running. Actually, Lucas is working the manuscript to put at least an application. So he is doing right now the control of the decay of correlations. So he's okay. He's done, but it's very ugly manuscript. We can share with you if you want. So, but we have the result, but it's not in the archive yet. And another thing is about the analysis, as you said. Maybe it's a good to share with you. So okay, the first thing that Lucas didn't mention it too much, but maybe you just come back in the beginning of the slides when you put the when you sit us our papers. Yes, okay. So so yes, in these 2 papers, alpha is bigger than D, right? Which is the best region possible, right? So even we discussed with Fanetter a lot of times. He in the beginning he didn't believe, but okay, of course, 1,000 of wrong proofs until the right one. So now we have the complete even for cluster expansion. So the one important thing that for the second paper we put the decay field, right? So we respect the pressure. The pressure is the same pressure as the zero field. So this is because of the graph is amenable. So in some sense, we one of the motivations of to do the cluster expansion, it was the beginning, was because you put the decaying field, but the pressure does not see the decaying field because the amenability of the graph kills the contribution of the field. But one maybe even more basic question in the direction that you said, during this investigation, we start to think about, okay, you have a Onzaga solution, you have this very sophisticated, let's say, exact solution of the models, and you have this in dimension 2. You know exactly the point where the pressure is not analytic, right? In dimension 2. So we asked, for example, for I think for Velianic, also for Ott, also for Giuliani, and about the if you know how to prove the pressure is not analytic in dimension 3 or plus in the phase transition point. You know how to prove this? So this is it seems very, yes, I want to ask for everybody. I don't know.
No, it's not about analytic continuation. It's about the following. The idea is how do you show that, for instance, for the Ising model, you know that the second derivative of the pressure that is related to the latent heat or something like that, yeah, it must, let's say, diverge on beta C. So can you prove this? This is the question. And then
yes, I mean,
or give an argument why this is.
Yes, I mean.
Of course, this is true. This is believed, but yeah.
So for the dimension 3 or more, yes, I asked for Alessandro Giuliani also. He said it's very natural, but he also doesn't know about. This is another, let's say, very natural question that we don't know. A lot of natural questions, but yeah, the cluster expansion we have now I mean our situation is the following. The result is very good, but it seems that since the objects are not connected, people are a little bit afraid of to be wrong, for example. So we are waiting now 3 years almost, let's say.
Yeah.
Okay, some other questions or comments or very challenging questions or no?
Yeah.
So let's take thanks Lucas again.
Okay.